15 of Complexity Explorer's MESA tutorial, Agent-Based Modeling in Python. In this session, we'll complete part 2 of our trade function in which we establish the marginal rate of substitution, or MRS, and price for our agents so that they can trade with each other. Let's get started. First, open up your preferred IDE or your Google Colab instance, and then we want to make sure your sugarmap.txt file has either been uploaded or is connected via your Google Drive through this mounting function. So import your dependencies. We do our helper function, which is get distance for this one. We do our resource classes, which is sugar and spice, which says that each one grows 1 unit per time step. Then we have our trader class, which is significantly longer, right? Where they move, they eat, they possibly die, and then we're working this function here, which is trade with neighbors. So far, we've established a list of neighbor agents that we could possibly trade with based off the agent's vision attribute, which tells how far they can see. Then we have our model class, which we initiate our model. This manages the interactions of our agents, so sugar, spice, right, and then traders using this kind of unique stage random activation function. Right, the agents move, eat, and die. That's what we call those functions, and then they trade with neighbors. Right, run that from session 14. We end up with the output of the length of neighbors that each agent has during one time step. So now we could delete this print statement, and now we want to create our actual trade function. So we need to iterate through our neighbor agents. So remember, neighbor agents is a list of agent objects. And if there is a trader agent object, then we're going to call our trade function that we're about to build. So we'll pass one parameter, which is the other trader agent that we want to trade with. Add a comment, just saying what we're doing here. Iterate through traders, right, and neighborhood agents. Remember that the neighboring cells is determined by the vision of that particular agent and how far they can see. Right, now I do need to account for something so you don't call this unnecessarily. Right, if the neighbor agents returns nothing, right, so it has no length, it's just an empty list, right, we don't want to do all these other functions. We want to end the function as it is. As we saw from the previous print statement, there are some neighbors that, or there are some agents that have no neighbor agents, right? So if that happens, if the length equals 0, or then we need to return the empty list, right? And this function will return two things. It will return the price or prices that the agents exchanged their sugar and spice at, and who they traded with, so we can monitor the trade network. So if that's the case, we'll just return two empty lists. So if length neighbor agents equals 0, then return empty list, comma, empty list. And now we want to build our trade function. So this is going to be def trade, right? And then it's going to have two parameters, one being self because it's part of the trader class, and the other one being uh, the other trader agent, right? So it's self or other, and that other being an agent object, a trader agent object. Right? Then put in our comments, right? So helper function, right? That's used in trade with neighbors, which is the main function we call from our model class. And then we're going to add, I got one comment here, which is just saying other is a trader agent object, just to emphasize that point. Okay. The other thing you could do here, right? So now we got hundreds of agents who are interacting with lots of other agents multiple times. So we're going to add just a sanity check here to make sure that they should be trading and the rest of our code's working properly. All right, so we're add Python's primitive assert function. It says if self.sugar is greater than 0 and self.spice is greater than 0, Then we'll do the same for the other agent, other dot sugar greater than 0, other dot spice greater than 0. Then that will allow this function to run. If it doesn't, if that assertion fails, then we'll get an error, and we know that there's some type of bug in our code that we need to check out. So this is just a sanity check to verify our code is working. Now that we've added this additional verification inside our model, the next thing we got to do is calculate the marginal rate of substitution of each of our agents. The marginal rate of substitution comes from microeconomic theory and determines how each agent values their sugar and spice commodity in relation to the other, and this is then based off each agent's unique biology, which is their sugar and spice metabolism. Right? There's a great description of this that starts on page 101 of Growing Artificial Societies and explains how Professors Axtell and Epstein developed the rules that they have for trading inside this particular model, and which what we're basing this off of. So we'll create a function called calculate MRS. Right? As you can see here, each agent object will have this function. So for self, we'll do self.calculate MRS, and for other, they'll use their MRS function in order to calculate their marginal rate of substitution. This is also then becomes important in just a sense when you're building a simulation, right? Just like data, you can make it say anything that you want. You can make a simulation say anything that you want, right? So it's important to make sure your simulations and models are built on firm theoretic foundations and that you're not just programming something to make it produce the answer that you want. Now that we've done that, we can look up here, right? So this is our calculate MRS, right? And on that similar vein, when we build our Cobb-Douglas function, right? Although I showed where a description of it on the internet, you can also look this up on page 97, which gives a great description of the integration of the Cobb-Douglas function and how they put it into this functional form, also in Growing Artificial Societies. Now the trick with that one is again, in the power of agent-based models, is that each agent is calculating their situation based on, or calculating their valuation, or based off their unique situation, right? So it's not a homogeneous view of every agent having the same situation. It's each agent being in a unique situation and then making decisions based off that. So appreciating the importance of adding theory and that agents allow for heterogeneous decision making based off their unique situation, we can now calculate the MRS or marginal rate of substitution. That will take one, so we'll create a helper function just above our trade function. That will take one parameter called self because it's part of our trader class. I had some comments here. And helper function for trade. And this is just going to be a pretty straightforward calculation based off the agent attributes. I'm going to add another line of comment here just to make sure we understand what it is that the marginal rate of substitution is, right? So super generically, just determines what the agent needs and what it's willing to give up, which based off the fact that they have sugar and spice and a sugar and spice metabolism, right? It's their need for sugar or spice and their willingness to give up the other commodity that they don't need, again, sugar or spice, right, in order to enhance their position so that they can hopefully continue to survive and thrive. And the function or the calculation is pretty straightforward. So we return self.spice divided by our self.metabolism of spice. And then this is going to be divided by self.sugar divided by our metabolism of sugar. So self.metabolism underscore sugar. And this will give us a number that's either less than or greater than 1 that tells us how much they, or if it's greater than 1, they have an excess of spice. And if it's less than 1, they would like some spice, right? So if they get it perfectly to 1, then they have reached a point where they neither care about sugar nor spice, right? They have enough of each, and enough of each and don't value one over the other. So now that that's done, so with calculate the MRS, we're going to return two float numbers. So similar to what we did previously, we want to compare these two float numbers, and so we're going to use the math.isClose function again. This will take the two parameters of the MRS of ourself and MRS of under, right? And then it's going to be, and then we're going to describe its tolerance, which we'll again do to two decimal places. So rel underscore TOL equals 1E-02. And then we're going to do a print statement just to make sure all this is working the way we think it should be. We're going to say print it was close, and if it was close, so we want to end the function, right? So if they don't, if the agents have a relatively close MRS, they actually don't want to trade with each other, and so we can stop that function there and create and prevent a bunch of unnecessary calculations. We run our model again, and we get I get a type error. It says rel2 is an invalid argument for is close. So we go back up to our is close function that we put in there because it should be rel underscore TOL. So we add that in there. I confirm that I didn't add a syntax error. Then we go ahead and run it again. Sure enough, we get it was close, so it seems to be working the way we think it is. At least we're not getting any errors. So now, from this, we can calculate the price. So again, if you start on page 101, in Growing Artificial Societies, you could get a very in-depth description over a couple pages of each of the choices and how and why these trade rules were set up. Right? But to calculate the price, we'll call it P, and it equals the math.square root, right, of the MRS of some itself times the MRS of the other. And again, this will give you a great description if you look at the trade rules in the book. Right? And then we're going to print the price to make sure that it's making sense and we're getting something reasonable for it. On this, we're getting prices less 2 and greater than 1, and we're not getting any assertion errors. So in the next lesson, we'll talk a little bit more about what that means. But through this lesson, we've established the marginal rate of substitution for each agent and calculated that in a price. Next, we'll have our agents potentially trade their sugar and spice in order to help their survivability. Thanks for joining, and we'll see you next time.